Hello, algorithmicians. Here we're going to be using the master theorem, and we're going to be learning how to find the constants from a real life algorithm. So hopefully you've already watched my video which explains to you how to just put the numbers into the master theorem, which is this thing up here on the top right. And now we're going to be looking at how we actually find the constants to put in. So let's start with merge sort. And you can see here we have a quick example of merge sort. We split the original set of data into two problems, and each problem is half the size. And that's what, if we take our numbers here, A and B, A is the number of problems which we've split the data into, and B is the size of each of these problems. So here we can see that A equals 2 and B equals 2. Now we have to work out, what does C equal? Well, let's just have a quick recap of how merge sort works. We split the data down into, so we've got 2 lots of n over 2. Now we've got 4 lots of n over 4. Now we've got 8 lots of n over 8. Now the merging process takes these same number of steps again. So whenever we're halving, we're going to end up with log n. We don't need to know that for the master theorem, but that's kind of what we're expecting. Now for each level, now that I'm merging, I have to do n calculations, or something times n to the power of 1 calculations, because at every merge step, I have to look at every single item of data. So that's why we know that C equals 1, because at every level we are doing n to the power of 1 sets of operations. So now we apply the master theorem. We say A equals 2, B equals 2, C equals 1. We compare A with B to the power of C, and we can see that A equals B to the power of C. So we're dealing with case number 2. And so our solution is from the second line of this thing here, which is going to be n to the power of 1 times log n. And hopefully that makes sense, because when we look at the theorem itself, whenever we're halving something, any kind of divide and conquer like that, we're probably going to be dealing with log n. So that's where we went from a problem of size 8 to size 4 to size 2. That suggests that we've got log n steps here. We've then got log n steps here. So that's 2 lots of log n, but we don't care that it's 2 lots of log n, it's just log n. Each of these steps, though, we have to do n lines of work to get from here to here, here to here, and here to here. And so that's why this idea of doing n times log n kind of makes sense. Let's see another example from an exam where it's kind of similar, but with a slight difference. Pause the video, have a quick read through. And what you can see, the difference here is that we're splitting into 3 sublists. So we're taking our original set of data and splitting it into 3. And then we'll do that until we get down to individual bits. And then we'll merge all of these back together. So pretty much the same algorithm, but splitting into 3. Now you notice here the version of the master theorem we've got is ever so slightly different, but that doesn't really affect anything. So we are splitting into A problems, into 3 problems. We're splitting into size of a third, so B equals 3. And we know from merge sort we're doing D, so the function is big O of n to the power of 1, so D equals 1. This is just a different version of the same problem. So now again we compare A and B to the power of D, and we can see that they are the same. So again, we've got case number 2, which is this case here, which means our solution is big O n to the power of 1 log n. So whether we split into 2, 3, 4 lists, we're going to get this n log n time complexity. Now, you might be wondering, how is it possible to get different values of A and B? Because surely if we split something into 3 problems, we're going to be reducing the size of each problem by a factor of 3. Well, no, that's not quite true. So in this situation, binary search is where we're looking for a particular item. In this case, we are looking for 8. And we have a sorted array. We split the array in half and we decide, is 8 bigger or smaller than the split point, the pivot point? So it's smaller than the first one, bigger than the second one, smaller than the third one, and it is in fact the fourth one. So in this case, we would say that A equals 1 because we're splitting this problem into one problem at each stage, but B equals 2 because each problem is half of the size of the previous one. In this case, C equals 0 because at each stage we're doing constant time work. We're not having to process through every item of data. We're just deciding, is the pivot greater or less than the data that we are looking for? So now we apply the master theorem. We're looking at A compared to B to the power of C. So we've got 1, we've got 2 to the power of 0, and we see they are the same. And so we're applying case number 2. Try that again. So we're applying line number 2, which means we have big O of n to the power of 0 log n, which is big O of log n, which is what we expect. We are dividing by 2 each time. We're not performing any real extra work outside of that loop. So big O of log n makes sense here. So that's an example where the number of problems and the size of each problem don't match up. Let's consider a problem where instead of having A being less than B, where we lose information, we have a situation where A is greater than B. So we might split the problem. We've got our set of data here. We might split it into, let's say, 4 parts, but each part is only half the size of the original set of data. And so in this case, we're going to have some overlapping. So rather than discarding some information, we're actually going to be using some of the information more than once. Now, this is quite a monster of a question. Pause the video, take some time to read through. Now, what does this actually mean? Well, when I'm doing matrix multiplication, we can see this is a divide and conquer problem. So let's say we have an 8 by 8 matrix. What we're saying is that we're going to, so it's 1, 2, 3, 4, 5, 6, 7, 8, etc. We're going to split this down into 4 by 4 matrices. So we're going to have A, B, C, and D, and each of these is a 4 by 4 matrix, 4 by 4, 4 by 4. And we're going to be multiplying this by another 8 by 8 matrix. So E, F, G, H. And we know from, well, how matrices work that when we do this, we take the rows and we take the columns. And for example, this top one is going to be AE plus BG. So this one is going to be found by multiplying matrices AE plus BG. The top right is going to be AF plus BH. The bottom left is going to be CE plus DG. and the bottom right is going to be CF plus DH. And what you can see here is that we've split 8 by 8 into a 4 by 4, so that's where this 2 comes from, but we're actually creating 8 subproblems. So 1, 2. So AE is a subproblem, BG is a subproblem, and we end up with 8 separate matrix multiplications. And you can see we actually use the matrices more than once. So we use each matrix, looks like we use A twice, B twice, C twice, D twice, etc. So we can see here that there are 8 matrix multiplications, which means that A equals 8. We can say that each matrix is half the dimension of the previous, which means that B equals 2. Now, the trickier part to work out here is why is it n squared? Now, the n squared is what's happening outside each of the loops, each of the multiplications. It's actually the addition, and the clue for that is this bit down here. So let's say we had an 8 by 8 matrix. So we started out with n being 8, and then we split that into 2 4 by 4 matrices. So we've got a 4 by 4 matrix here, and another 4 by 4 matrix here. So each of these matrices were n by 2, n divided by 2. Now, how many operations do we need to do to add 2 4 by 4 matrices? Well, it's actually 16 operations we need to do. So it's n over 2, because we went from 8 to 4, and then it's that thing squared, which is going to give us big O of n squared. We ignore the fact it's n squared divided by 4. So that is where we get this part of the recurrence relation from. So those are the bits we need to explain. We need to explain that every matrix is split into 8 subproblems because there are 8 different multiplications. We're dividing each one by 2 because each matrix is half the dimension of the previous one. But then outside each loop, we're doing n squared over 4, which is big O of n squared, to get that n squared after the recurrence relation part. So that's how we get those 3 marks. Now, if you were doing this in an exam and you didn't completely explain that, doesn't matter because we are now just applying the information. So A equals 8, B equals 2, and C equals 2. We use our master theorem. We're comparing A with B to the power of C, and we can see that 8 is greater than B to the power of C. We go back to our previous slide with the master theorem, and we can say it's going to be big O of n to the power of log B A, which is going to be big O of n cubed. Let's read through this algorithm, and it took a few goes for me to really see what was going on here. So let's start with a simple example. Let's have a power of 2, so 2, 4, 13, and 20. That's our array, so that is members, and we'll assume we're indexing from 1, so we've got indices 1, 2, 3, and 4. So the first call we do is MT between 1 and 4. Here we find the midpoint as 2, and then we're doing a couple of recursive calls. We're going to call MT from 1 to 2 and MT 3 to 4. For this first recursive call, we get a midpoint of 1, which means we're going to call mt of 1 to 1 and mt of 2 to 2. Very similar thing over here, midpoint equals 3, so we get 3 to 3 and 4 to 4. Now for each of these, because the boundaries are the same, we are going to return 1. This one we return 2. This one we return 3. This one we return 4. So we're now back up to the second line of recursive calls, this line here. And we're considering this part of the code. So we've gone back, we've got the numbers 1 and 2, and we're saying if the index at 1 is greater than the index at 2, we return 1. If not, we return 2. So in this case, we are returning 2. We're returning the index that has the bigger one. And over here, we are returning 4, the index that has the larger one. That gets returned up here, and we compare the index at 2 with the index at 4, and so we return 4. And that is our final answer. So that tells us member 4 was the member who played the most matches. Okay, so the design pattern using here, we can see this is a divide and conquer. It's 1 mark. If you said decrease and conquer, that's not right, because we're not making the problem any smaller. Okay, now for part B, we need to explain how this time complexity comes about. I'll leave that diagram there. It might look a bit messy, but I'll write here in red. So we've divided into, so each stage divides into 2 problems. That means that A equals 2, and each problem is half the size of the previous level, which means that B equals 2. 3 marks here. We also need to explain why is it +1. So we're told in the thing that this is working in constant time. So the comparison at each stage is constant, which means that C equals 0, okay, i.e. big O of n to the power of 0. And then we would put all that into the master theorem, and we would find that we get big O of n. So hopefully, folks, you've seen now how we can identify the numbers A, B, and C from a real algorithm and put them into the master theorem.